Today topic of discussion is mass energy equivalence. This is mass energy equivalence. This mass energy equivalence relationship basically is very important because this was derived by Einstein from the postulate of the special theory of relativity. So that's why this mass energy equivalence relationship is important, and it's have very much physical significance also. So in order to drive basically this relationship, let us consider a particle, and this particle is of mass m naught at the rest position. So this is a particle of mass m naught. It attain mass m. This basically attain mass m when we apply a force on it, and it basically starts to move in this direction, in the direction of the force. If by the force of F this displace a small distance, suppose that is dx, then the work done on it can be defined as dw is equal to F dot dx. But as a result of this force, this particle displaced from position A up to the position B. This is position B, and this distance is basically x from A to B. So we have to find out the kinetic energy of this particle from A to B. But before that, this particle is displaced a very small distance, that is dx. So the amount of work done from A to this position, that will be dw is equal to F dot dx. Now theta, basically this is the scalar product between the displacement and F, and theta is equal to 0 because this is parallel. So this can be written as F dx simply, and this is a small work done. We know basically from the Newton's second law, this is F is equal to dp upon dt in terms of the rate of the momentum, where p is equal to mv. M is the mass when this particle basically accelerates. V is that velocity. So F can be written as F is equal to d mv upon dt. And now instead of this F, one can write here d mv upon dt into dx. This is dw in terms of m and v. Further, one can rearrange the terms. We can write now this dx upon dt and this dmv, and this dx upon dt is equal to v. So dw, work done from this origin to up to this very small distance, that is dw, and this dw basically appear in terms of the kinetic energy. So dw is equal to dk, that work basically done on this particle appears in terms of the kinetic energy by which this particle start to move basically. So this dk is equal to dx upon dt is v and dmv. And if suppose I want to find out the total work done from point A to B, then I have to integrate it from 0 to x. Limits will be x is equal to 0 to this x. So now the total work done, that will be total kinetic energy, will be 0 to V, and in this case that limit will be 0 to x up to this. So this is 0 to x right now, and this is total work done. Total work done is basically appear in terms of the kinetic energy. So this is kinetic energy. Now we have kinetic energy of the particle, and that formula is kinetic energy is equal to 0 to V, limit of integration, and this V dmv. So now we have to solve this integration, but before that we have to make some correction here. That is m, we know, is equal to m naught upon square root 1 minus v square upon c square, where m is naught is the rest mass, and m is that mass basically which appear when we apply the force on it. So this is that m during the motion. So m is equal to m naught upon square root 1 minus v square c square, and further this factor 1 upon square root 1 minus v square upon c square can be written as gamma. So now I can write here m is equal to gamma m naught, and instead of this m here I can use this gamma m naught, where gamma is a function of v. So this equation can be written as m naught, this m is equal to m naught gamma. M naught is rest mass, that is a constant, so comes out from this integration, and this is 0 to v, and this d gamma and v. So now we have this integration, and in this integration both gamma and v, gamma is also a function of v, both are variable, so we have to differentiate this d gamma v first of all before we solve this integration. So d gamma v will be equal to, these are two factors functions f1x, like f1x f2x, so we have to differentiate both of the. So this can be written as gamma dv plus v d gamma. This is simple case, but now we have to solve this d gamma. So that d gamma comes from here. So this gamma is a function of v, and so first we will differentiate this. So we have to find out d gamma upon dv, and that will be d upon dv, and this factor 1 upon square root 1 minus v square upon c square. So we have to differentiate this one. So to make it simple, I just can assume e square 1 minus v square upon c square, or I can solve it directly. So this can be written as d dv 1 minus v square upon c square minus 1 by 2. So this 1 minus v square upon c square minus 1 by 2, differentiation of it. So first that will be is minus 1 by 2 of this factor 1 minus v square upon c square, differentiation of it, that means n minus 1, so minus 1 by 2 minus 1, that will be minus 3 by 2, and then differentiation of this factor, that will be minus 2v upon c square. So minus and this minus is plus, 2 and this 2 cancel out, so we have this v upon c square 1 minus v square upon c square minus 3 by 2. So now we can put the value here. So this d gamma v is equal to this gamma dv. Now I am putting the value of this gamma here. So this is dv upon square root 1 minus v square upon c square. This v d gamma, this is d gamma now, and d gamma upon dv. So d gamma is equal to v upon c square and this dv. I need only d gamma, so dv goes here. So v is already v square, and this is dv upon this factor c square, and this 1 minus v square upon c square, and now this is 3 by 2. So now I am putting the value of this d gamma from here. This is d gamma upon dv, that is equal to this factor. So d gamma will be equal to this factor multiplied by dv. So I put that value d gamma here of this here, and now further I am taking the, and this is plus, I am taking the common this dv upon this 1 minus v square upon c square 3 by 2, and this is 1 by 2. So taking common this dv upon 1 minus v square upon c square, and this 3 by 2. So dv common, and this is 1, and this is 1 by 2. I am taking 3 by 2, so 1 by 2 minus 3 by 2, that will be minus 1 minus 3, that is minus 2. Minus 2 divided by minus 2, that is minus 1. So here I am getting 1 minus v square upon c square minus 1. That can be written as, this is 1 upon, I am writing here directly, not directly, but for not skipping this step, so I am writing 1 minus v square upon c square, this minus 1, and plus this v square upon c square, because I have already taken the common dv upon this factor 1 minus v square upon c square raised power 3 by 2. So this is v square upon c square, and now after simplification of it, the result will be, I got this d gamma v is equal to dv upon 1 minus v square upon c square, that is power 3 by 2, and that factor 1 upon 1 minus v square upon c square minus 1, this can be written as 1 minus v square upon c square, and this factor plus v square upon c square, so v square upon c square. Now I have v square upon c square cancel out, so I have this dv upon 1 minus v square upon c square 3 by 2. So as a result of this d gamma v, I have only this term. this cancel out, this is equal to 1. So d gamma v is equal to dv upon 1 minus v square upon c square, and this 3 by 2. So now I have to put this value into this particular d gamma v is equal to this one. So this was here into this particular integration. So now I have to put the d gamma v value here in the formula of kinetic energy. So kinetic energy formula is equal to 0 to v d gamma v, and now I know the d gamma v value, and this is, I can put here this m naught is also. So m naught 0 to v, this v and this dv, v dv upon this 1 minus v square upon c square 3 by 2. Now I have to solve this integration for the kinetic energy. For that purpose I can assume that this 1 minus v square upon c square is equal to x. So I want to solve this integration first of all. So 1 minus v square upon c square is equal to x. Suppose I can put this value here, and further I will differentiate it with respect to v. So this minus 2v upon c square is equal to dx upon dv. So d this minus c square upon 2 dx, this c square and minus 2 this one dx is equal to v dv. So I have this v dv. If I put the value of v into this one, when v is equal to 0, this x is equal to 0, and when v I am putting this x is equal to v, to almost same. So I am writing here kinetic energy, that is equal to m naught, and this integration v dv, that is minus c square upon 2. So minus c square upon 2, and this dx, instead of v dv I am writing here minus c square upon 2 dx upon this factor is x. So x 3 by 2. Now limit will be 0 to x, you can say right now, or you can basically I have to use this just for simplification of this integration. So ultimately I have to use this velocity limits for the kinetic energy, but right now this is differentiation with respect to x, so I can to use this 0 and x, but for the purpose of this solution, first I am solving this integration, and limit I will take 0 to b as usual. So this minus m naught c square upon 2, and this integration 0 to v x minus 3 by 2 dx, and now the integration of it, that will be of the result kinetic energy is equal to minus m naught c square upon 2, and integration of this x minus 3 by 2, integration of x n dx is equal to x n plus 1 upon n plus 1. So here n is equal to minus 3 by 2, So x minus 3 by 2 plus 1 minus 3 by 2 plus 1. So this becomes x minus 3 by 2 plus 1 upon minus 3 by 2 plus 1 is equal to 2 minus 3 plus 2, x minus 1 by 2, and this is minus 1 by 2. So further simplification of it, then the result will be minus m naught c square upon 2 and again minus 2 upon 1, this factor from here, yeah, minus 1 2, and this x minus 1 2 I can write here, and x I know is 1 minus v square upon c square. So this 1 minus v square upon c square minus 1 by 2 divided by minus 1 by 2. So this can be written as minus 2 upon 1, it comes out, and this x minus 1 by 2 is equal to square root 1 minus v square upon c square, and limit 0 to v. So this minus 2 cancel out, minus minus plus, so I have this m naught c square. Now I put the value v, 1 is square root 1 minus v square upon c square, and minus v is equal to 0, and this is 0, so this is 1 minus 1. Now the result is m naught c square upon square root 1 minus v square upon c square minus m naught c square. We know that this factor m naught and this is m, so one can write here instead of this m, so m c square minus m naught c square. So now the kinetic energy is equal to mc square minus m naught c square. We know that kinetic energy is equal to total energy minus rest mass energy, that is potential energy. This is kinetic energy. So total energy E represented by E is equal to mc square, and rest mass energy, this is total energy E, and rest mass energy, that is potential energy, is equal to m naught c square, and the difference of the total energy and potential energy, that will be kinetic energy. So this formula is for the relativistic kinetic energy. This formula is for the relativistic kinetic energy. Kinetic energy is equal to mc square minus m naught c square. While in classical mechanics we know that kinetic energy is equal to 1 by 2 m naught v square. This is the classical kinetic energy in general which we observe, 1 by 2 m naught v square. But in relativity we are observing in terms of the relativistic mass, rest mass, and speed of light. So this is our kinetic energy, mc square minus m naught c square. So how to get, what are the limitations basically for it? For that we know that this at a very low speed, basically what will happen at very low speed, when V is very small as compared to the C, then the relativistic expression for the kinetic energy reduced to the classical kinetic energy, that is 1 by 2 m naught V square. So how to find out this result? Now we know that kinetic energy that is represented by T is this is the kinetic energy. T is equal to total energy mc square minus m naught c square, that is rest mass energy. mc square, writing it properly, m is equal to m naught c square upon square root 1 minus v square upon c square, and this is minus m naught c square. When v is very less than c, in this situation what will happen? We have this factor 1 upon square root 1 minus v square upon c square, and this can be written as 1 minus v square upon c square minus 1 by 2. If I expand it binomially theorem, according to the binomial theorem, so this will be 1 plus v square upon 2 c square plus 3 by 8 v4 c4 and so on. So now if I put this value here, so this becomes m naught c square and this vector. So kinetic energy T is equal to m naught c square, this 1 plus v square upon 2 c square plus 3 by 8 v4 upon c4 and so on, and minus this term minus m naught c square. We know that here our condition is v is very small as compared to c, then this term is negligible and we can write only this m naught c square plus m naught c square v square upon 2c square plus this m naught square c square v3 and this v4 upon 8c4 up and so minus m naught c square. We know that this v is very small as compared to c, so we can ignore the second term. M naught c square, this one, and minus m naught c square cancel out, so we have only this term, that is c square, this cancel out, m naught v square by 2, this is m naught v square by 2, 1 by 2, so t. So this is the limitations of this relativistic kinetic energy formula. So we can get, or one can get, this kinetic energy T is equal to 1 by 2 m v square. So this result is in classical mechanics when speed is very low, but when speed is comparable to the speed of light, then we have to use this formula. T is equal to mc square minus m naught c square, and this formula for very small velocity as compared to the speed of light. So these are known as the limitations of the kinetic energy, relativistic kinetic energy.